Hello, welcome back to another video log recording session where I talk about genetic algorithms, the very basic stuff, what I have learned, what to do, what not to do, etc., etc., and rant on about my thoughts. They can be somewhat philosophical, but not at a high level, so that's okay. Well, might not be okay. The date is 2025, March the 3rd. And in this Jupyter Notebook file named genalgo2, I will be talking about how a fixed initial population that is full of zeros or genomes that are just zeros, or what I call void genes, can also lead to good evolution, or some kind of an evolution that does manage to generate solutions. So you don't really need, you might not really need the random gene generator that I used, that I have used before. So I might need the random gene generator, I might not. I'm just trying to see what I can do or what I cannot do. So in this notebook, I'm going to do without the random gene generator. I'm going to fix the initial population of entities and as an initial pool of genomes that are just made of zeros, as in no items selected, but then each generation is going to go through mutation, every mutation on every element level, and that somehow also does reach some kind of an evolution. So that's that. Let's start. So run that, all the same stuff, all the same items, all the same utility values, constraint values, all the functions are the same. It's just that I won't be using some of them, and the only hyperparameters are the same. Max constraint is 4000, so that's the threshold. Population size is 500. Number of items and genome length is 20, as in 20 items, and 20 corresponding utility values and constraint values, or just physical weight values. So run that, and let's initiate the evolution. Also, and in this notebook, it is important to note that I used I've altered the values for the weights at which the entities will be chosen as parents, or likely to be chosen as parents. I'll be dividing each weight of the entity by these numbers. I'll just quickly show. So divide, for example, if the population is 500, divide 500 by 1, that will be the weight for the first entity. Divide that by 2, that will be the one for second entity. Divide that by 3, that will be the one for third entity. So 500, so that will be something like this: 500, 250, 166, 125, 183, etc., and on and on and on and on. So I run that. That should take about, again, 90 seconds probably. I'm just gonna check. Yep, 24 seconds. Maybe I ran it on my laptop, not Colab, which is why it said 24 seconds. There's no way this runs within 20 seconds, within under 30 seconds on Google Colab on the very basic setting. So we wait. Generation 1600, so past the halfway point. And previously, if we look at the result, the highest one was 690, so kind of good. Again, I'm always saying the best is 710 under these circumstances, so 690 is on the good side, in quotes, good side. Again, we don't know what is good. This is good in this context, but things change. So again, around 90 seconds. 92 seconds. This time it's again 690. Cool. Yep. So somehow the void genes have managed to reach a level where it is, acceptable as an answer. And they have reached a level where the population does have some very decent answers. Not the best, but quite decent. So let's try that again. Another 90 seconds. We are starting with void genes, just full of zeros. One-third way done. Another note that I should make to myself is, in the future, it might serve as some benefit to study the distribution of entities in terms of their summed utility values, because even when I do have one or two entities with very high scores, I'm not going to get a lot of them. Naturally, I would assume, or I could assume, that it's going to have some kind of a normal bell-shaped curve, but I haven't actually found that out yet, so I can do that next time. 645, so that's not so decent. Last time it was 690, now it's 645. So this time is a bit of a failure. Let's try one more time, and then if it doesn't work this time either, I'll have to change the way the weights are created, so that it becomes this, so it allocates the same weights as the previous recording session, where the weights equal number of population divided by 1, 3, 5, 7, etc. and on and on and on. the meantime, I'm just going to have a look at the temperature of my CPU. It is around 59 or just about 60 degrees Celsius, so it doesn't get that hot. Although I imagine I'm using a lot of CPU. Oh wait, that's because I'm not actually using my CPU. I'm using the computation on Google Colab, so that's why. I'm so dumb. Now it's 680. The best one is 680. So that's still decent, but could be better. So let's try change this so that the entities with higher scores get to reproduce more, or are more likely to be chosen as parents. Remember, it was 690, 650, was it? Or 645, 650, or was it 640? And then it was 680, so about 670, 665 on average. And then it was 680, so it's about 670 on average. Okay, again, 92 seconds. 700. Yay. That was cool. Now we have a 700. So, in this case, it does seem that altering the weights have created or have enabled us to create entities with higher scores. But again, I have to mention that because I've done more work after this, I have to mention that that may not always be the case, and I need a way to ensure that this keeps on happening. Let's try one more time and see if I can get 710. Right now, this is not pre-recorded. I don't know what's going to happen. I might get anything around 700, but I'm not. The perfect one, 710, isn't guaranteed. Again, perfect is also subjective. Let's always keep that in mind. I mean, 92 seconds is kind of long. point of this notebook again is to find out if starting with an initial population, the genesis with empty or void genes, is a smart thing to do, is a viable plan. And so far it does seem like it does. 705. So that's good. That's decent. Do I want to try again? Maybe not. It's too long. I mean, I think I've proven my point. So that's that. Thank you for watching. Bye.